Imagine you have two dead satellites, like each the size of a school bus, right?
Yeah.
And they are just hurtling toward each other in low Earth orbit at roughly 15 kilometers a second.
Yeah, 15 kilometers a second is, I mean, it's almost hard to wrap your head around that speed.
It is wild. And you have a standard laptop, a fresh Python environment, and let's say about 50 lines of code to figure out if they are going to violently collide sometime in the next 24 hours.
Which sounds completely impossible.
Right. Sounds totally impossible. But it's actually not.
No, it is entirely possible. Provided you are willing to completely rethink how a standard software application is supposed to work. Because when you're dealing with objects moving at orbital velocities, the margin for error just vanishes. And normal computing rules, well, they just break down.
Which brings us to our mission for this deep dive. We are taking a really fascinating stack of transcripts and code notes from a show called the Pythonic Orbit.
Oh.
And we are going to give you, the listener, a complete blueprint for building your very first orbital tracking project.
Yeah, a fully functional space domain awareness pipeline.
Exactly. But to pull this off, to get those 50 lines of code working, you really have to embrace some wildly counterintuitive architecture. So, okay, let's unpack this, because the very first hurdle isn't even about physics.
No, it's not.
It's about programming languages. To track a satellite, you need a high-fidelity physics engine, and the absolute gold standard for spaceflight dynamics is a library called Orekit, the catch. It is natively written in Java.
Which is usually the last thing a Python developer wants to hear.
Seriously.
I mean, if you are building a Python script, you expect a certain workflow, right?
Yeah.
You open your IDE, you type pip install, you import the library, and you're off to the races. It's a clean, isolated, deeply satisfying sandbox.
And everything just works.
Exactly. You do not want to stop everything to go wrestle with Java environment variables or cross-language configurations.
So to bridge that gap, the community created an Orekit Python wrapper. But diving into the source code, this isn't just a standard Python module where you call a function and it runs some native C code in the background. The very first line of code you have to execute before you load a satellite, before you do a single math equation, is orekit.ituam, initialize the virtual machine.
Yeah, and that one line is doing some extremely heavy lifting. It is dynamically allocating memory and actually spinning up a full Java virtual machine, a JVM, inside your active Python process.
Wait, inside the Python process?
Inside of it, yeah. Python is essentially acting as a puppet master, pulling the strings of this massive Java engine.
And there's a trap here, isn't there? The show notes emphasize that this initialization is a strict one-and-done command.
It is an absolute architectural constraint. Once that JVM is awake inside the Python session, it cannot be restarted or reinitialized.
So if you mess it up
if you try to run that command twice in the same script, or if you try to reset the environment without fully killing the Python kernel, the whole process just crashes. You have one shot to boot the brain.
Okay, so it's like we've turned on the brain, but the brain is completely blind. Because looking at the setup, why does this super smart industry standard physics engine require us to immediately download and feed it a random zip file before it can do basic addition?
Because basic math and orbital mechanics requires physical context. You cannot ask an engine where a satellite will be located relative to the Earth tomorrow without mathematically defining what the Earth actually looks like tomorrow.
Right, and the Earth isn't just some perfect, smooth, geometric sphere spinning predictably like a toy top. The sources use a fantastic term for this. They say the Earth is a lumpy potato.
It is a remarkably lumpy, dynamic potato.
I just love that visual.
It's accurate. The Earth's gravity isn't perfectly uniform. A satellite feels a slightly different gravitational pull flying over, say, the dense rock of the Himalayas compared to flying over the deep Marianas Trench.
Oh, wow. So it actually feels the mountains.
Absolutely. And on top of that, the Earth actually wobbles on its axis. Its rotation speed constantly fluctuates by milliseconds due to massive oceanic tides shifting, tectonic plates moving, and even atmospheric weather systems dragging against the mountains.
Like, really, the weather literally slows down the planet.
It does. And all of those tiny, constantly shifting physical realities drastically affect the trajectory of something orbiting in space. So to calculate high-precision trajectories, Orekit needs a massive, constantly updated contextual data set. Earth orientation parameters, leap second history, complex gravity fields, all of it.
And you obviously can't hard code that into a software library because the planet is changing every single day.
Exactly.
So as the developer, you have to provide it. The Orekit team maintains a zip directory for this, usually called orekitdata.zip, and the Python wrapper gives you a helper function to set it up. You just point it at that zip file. But I want to clarify what happens if you skip this step. The notes mention a null pointer exception.
Yeah, it's a bad one.
For a Python dev, that might just sound like a generic bug, but in this context, it's a nightmare, isn't it?
It is the ultimate rookie mistake. In Python, when something breaks, you usually get a helpful traceback pointing to the exact line of Python code that failed. But if you forget to feed the lumpy potato data to Orekit, the failure happens down inside the Java virtual machine.
Oh, I see.
Yeah, your Python debugger cannot make sense of it. It just spits out this massive opaque Java stack trace that is absolutely terrifying to look at.
Just a wall of red Java errors in a Python script.
Precisely. You avoid all of that by simply pointing the engine's data context to the zip file. You give the blind brain its sight.
Okay, so the engine is awake, and it understands the physical quirks of our lumpy planet. But knowing how the Earth behaves doesn't really help us if we don't know when we are looking at it or where to put our satellite. The sources make a huge deal out of meticulously defining the environment first.
Because environmental definition is everything in space domain awareness. And time is, well, it's the most perilous variable. Time in orbital dynamics is vastly more complicated than time on your wristwatch or your computer system clock.
Because if I'm writing Python, my immediate instinct is to reach for the built-in datetime module. I just set it to UTC and call it a day. But UTC is fundamentally flawed for tracking objects in space.
It really is. It comes down to leap seconds. UTC, Coordinated Universal Time, is designed to keep our human clocks aligned with the daylight. And because the Earth's rotation is gradually slowing down, authorities periodically inject a leap second into UTC to keep noon happening when the sun is actually highest.
But think about the math of a satellite moving at 15 kilometers per second. If you are integrating a timeline and suddenly your clock just hiccups, it stops for a full second or jumps backward, your satellite just teleported 15 kilometers in your simulation.
Exactly. You completely destroy your spatial continuity. A 15-kilometer calculation error means you either predict a massive collision that never happens, or far worse, you completely miss a disaster that does.
Right, which defeats the whole purpose.
Exactly. That is why Orekit explicitly prevents you from doing physics with standard datetime objects. You have to use an object called an absolute date.
An absolute date. So how does that fix the leap second problem?
Well, an absolute date represents a unique, continuous instant in the universe, totally independent of any specific human timescale. To bridge the gap, you use Orekit's timescales factory. You feed your human-readable UTC time, year, month, day, hour, into the absolute date constructor.
Okay, so you still use human time to start.
Right, but under the hood, Orekit anchors that specific instant to continuous physical timescales, primarily International Atomic Time, or TAI, by bypassing the UTC leap seconds entirely.
And atomic time doesn't care about the sun or the daylight. It just counts the decay of atoms, completely ignoring leap seconds. It just ticks forward relentlessly.
Exactly. So your timeline remains perfectly smooth, which keeps your math mathematically sound.
Brilliant. So we know when we are. Now we have to define where space is. And this brings up coordinate relativity. Telling someone a satellite's coordinates is completely useless without an agreed-upon reference point.
Very true.
If my reference point is a radar station sitting on the ground, that's like trying to measure the speed and trajectory of a runner on a track, but I'm trying to do the math while spinning around in circles on an office chair.
That is a highly accurate way to visualize it, because the Earth is spinning. In orbital dynamics, that rotating reference point is called the International Terrestrial Reference Frame, or ITRF. And if you plot a satellite's trajectory relative to the spinning ground, the satellite looks like it's flying in a bizarre, chaotic, squiggly pattern over the map.
But satellites don't fly in chaotic squiggles. They fly in smooth, predictable ellipses governed by gravity. So to see the real physics, we have to stop the office chair from spinning. We have to remove the Earth's rotation from the math entirely.
Yes, you do. For collision analysis, you need a frame of reference that is centered on the Earth's core, but it remains absolutely fixed against the distant background stars. It does not rotate with the ground. This is called the Earth-centered inertial frame.
And looking at the code snippets, we do this using Frames Factory. We pull a very specific non-rotating inertial frame called EME 2000. So the stage is finally set. We have our continuous atomic clock, and we have our non-spinning arena. Now we need the actors, we need the actual satellites. And this just blew my mind. Tracking modern, multi-million-dollar space hardware relies on a legacy data format from the 1970s.
Ah, yes, you're talking about two-line elements, TLEs.
It is wild to me. These are literal strings of text originally designed to be punched into 80-column IBM punch cards. Just 2 lines of dense alphanumeric gibberish that somehow completely encode an object's orbit.
It may be a relic of the Cold War, but I mean, it is an incredibly efficient way to share massive amounts of data. You can go to a database like Spacecrack right now and download a single text file containing the bulk TLE data for every active satellite and piece of tracked debris in low Earth orbit.
We're talking tens of thousands of objects represented in a few megabytes of text.
Exactly.
And here is where using Python really shines. Python is world-class at parsing raw text. You can scrape that spacetrack file, grab the specific 2-line string, say, for the International Space Station, and pass it directly into Orekit's TLE object.
And the moment you instantiate that object, Orekit unpacks the punch card. It instantly understands the mean motion, the eccentricity, the inclination. It basically builds a complete geometric profile of the orbit in a fraction of a second.
So we have our mathematical satellite hovering in our virtual space, but as the sources are quick to point out, a TLE locked to an absolute date is just a snapshot. We know exactly where it is right now, but if we want to predict a collision 24 hours from now, a snapshot isn't going to cut it.
No, it's not.
We need a movie. We have to hit fast forward.
And the process of moving a satellite forward or backward in time along its trajectory is called propagation. And Orekit offers 2 vastly different ways to do this: numerical propagation and analytical propagation.
Let's dive deep into this because this choice dictates the entire architecture of the script. Numerical propagation sounds like the ultimate high-fidelity approach. It steps through time, microsecond by microsecond, calculating every single physical force acting on the satellite. It factors in the lumpy gravity, the atmospheric drag molecules hitting the solar panels, solar radiation pressure, even the gravitational pull of the moon.
Yeah, it integrates all of those microscopic physical forces to constantly update the satellite's exact position and velocity. It is definitively the most physically accurate way to model an orbit.
Wait, hold on. If numerical propagation is the most physically accurate and we are trying to predict catastrophic collisions where human lives or billions of dollars are at stake, aren't we sacrificing safety by not using it? Why would we ever consider using the alternative, analytical propagation?
It comes down to the brutal, unforgiving reality of compute constraints. If you are NASA and you are planning a single thruster burn for the James Webb Space Telescope, absolutely you use a numerical model. But our mission is space domain awareness. We aren't looking at one satellite, we want to check 10,000 satellites against each other.
Ah, okay, so the scale completely changes the math.
Radically.
Yeah.
If you try to run a high-precision numerical integration, calculating billions of microsecond force interactions for every possible pairing of 10,000 satellites, your local laptop CPU is going to just grind to a halt. It would take weeks to process a 24-hour forecast.
Right.
That is where analytical propagation saves you.
So how does analytical work if it's skipping the step-by-step force calculations?
Well, instead of integrating physical forces over time, an analytical model uses extremely complex closed-form mathematical equations to predict the position. It's like a cosmic shortcut. You plug your target time into the equation, and the equation instantly spits out the location. It skips all the steps in between, which makes it exponentially faster.
But is a mathematical shortcut actually accurate enough for collision avoidance?
This is perhaps the most critical insight in the entire space domain awareness field. Remember our punch cards. Because we chose to use TLEs as our data source, the choice of propagation was actually made for us. TLEs are not raw, exact physical coordinates. They are what orbital dynamicists call mean elements.
Okay, mean elements.
Yeah, they have been mathematically smoothed out, specifically designed to be paired with one exact analytical model, simplified general perturbations number 4, or SGP4.
Wait, so feeding this TLE data into a more accurate numerical physics engine actually makes the result worse. That breaks every rule of standard data processing. Usually, better processing yields better results.
It is entirely counterintuitive, but it is absolutely true. TLEs and SGP4 are a package deal. The errors in the TLE format are intentionally designed to cancel out the mathematical simplifications in the SGP4 algorithm. If you take a TLE and feed it into a hyper-accurate numerical model, you rip them apart. The mathematical harmony is destroyed, and your calculations will actually be vastly less accurate.
Okay, let's unpack this. Here's where it gets really interesting. You have to use the right key for the right lock. So, practically speaking, how do we build this SGP4 engine in our Python script? According to the code notes, Orekit makes this absurdly easy. It takes exactly one line. You call TLE propagator dot select extrapolator and hand it your TLE object.
The architecture really is brilliant. The library automatically reads the TLE, recognizes the legacy format, and builds the SGP4 analytical model in the background without you having to manually configure a single mathematical variable.
So your fast forward button is fully built. Now, you just time travel, you create a new absolute date for your target time tomorrow. You call the dot propagate method and hand it that future date, and instantly the engine returns a state object for that precise millisecond in the future.
But keep in mind, a state object contains a massive amount of metadata that we don't necessarily need.
Right, for a collision check, I don't care about the orbital inclination tomorrow. I just need physical location. I need X, Y, and Z. So we extract the PV coordinates, position, and velocity, and Orekit hands us those raw Cartesian coordinates in meters.
And those X, Y, and Z coordinates are relative to the non-spinning EME 2000 inertial frame we anchored earlier.
Exactly. And here is the real payoff of doing all this inside a Python wrapper rather than pure Java. We have raw numerical data. We can take those X, Y, and Z coordinates and drop them straight into a pandas data frame or a massive NumPy array, leveraging all the data science tools Python is famous for. Which brings us to the ultimate question. We know exactly where satellite A and satellite B will be tomorrow. Do they hit each other?
Mathematically, finding out if they hit is just finding the Euclidean norm of their position difference.
Hold on, Euclidean norm. Let's translate that for the non-mathematicians. We are just talking about taking out a giant cosmic tape measure and finding the straight line 3D distance between satellite A and satellite B at any given second, right?
Yes. Basic three-dimensional geometry. You subtract the coordinates, square them, sum them, and take the square root. The math itself is trivial. But once again, we run face first into a computational brick wall.
Let me deduce this, because if I approach this like a standard Python developer, I'm going to write a for loop. I'm going to loop through every second of the next 24 hours. And inside that loop, I'm going to write another loop to check satellite A against satellite B and satellite C and so on. If I have 10,000 satellites, that's big O notation nightmare fuel.
Oh, absolutely.
I mean, won't writing a bunch of nested Python loops to process billions of distance checks make my CPU literally cry? It's just too slow.
Python loops are notoriously slow because Python is an interpreted, dynamically typed language. If you try to brute force a conjunction analysis that way, you will never get an answer. You have to be smarter about your system's architecture.
So my instinct as a data guy is to abandon Python's built-in loops entirely. I dump all those generated coordinates into a massive NumPy array and use vectorized CMath to filter out all the obvious noise. Is that what the sources mean by a two-phase architecture?
That is exactly what they mean. The first phase is what orbital dynamicists call the broad phase filter. You do not check every single second. That is a massive waste of compute. Instead, you use a fast time step. You sweep through your 24-hour forecast window sampling, maybe once every 60 seconds, and as you said, you use vectorized arrays in NumPy or SciPy.
Because NumPy handles those arrays in compiled C code using contiguous blocks of memory, which is lightning fast compared to a Python for loop.
Precisely. You do this massive sweeping calculation across all 10,000 objects just to find windows where objects drop below a safety threshold, let's say 10 kilometers. If the vectorized math shows that two satellites never get closer than 10 kilometers during that 60-second step sweep, you discard them from the memory block entirely.
They are safe. We don't care about them anymore. But what happens when that fast vectorized sweep flags a 60-second window where two school bus-sized chunks of metal actually do cross that 10-kilometer threshold?
That trigger initiates phase 2, the find phase search. You stop sweeping the whole catalog. You isolate that one specific pair of satellites, and you isolate that one narrow 60-second time window. Now you zoom all the way in with high resolution.
Now we check second by second or even millisecond by millisecond, and we can do this safely because we are only running the heavy calculation on a tiny sliver of data. And Orekit has a native method for this tape measure math, right? Vector 3D dot distance.
Yes, it handles the 3D geometry flawlessly. You step through that dangerous 1-minute window, calculating the exact distance at every millisecond, watching the numbers shrink until you find the local minimum.
The absolute closest those two objects ever get to each other before they start drifting apart again.
In the industry, that specific minimum distance is called the mist distance, and the exact millisecond that the mist distance occurs is logged as the time of closest approach, or TCA.
Mist distance and TCA. If you are building a space domain awareness pipeline, those are your two golden metrics. Everything we've done serves those two numbers. And looking back over the companion code provided in the source, by utilizing this specific two-phase architecture, the broad vectorized sweep followed by the fine-grained Java zoom, you can genuinely build this entire functional system in under 50 lines of Python code.
It is a masterclass in leveraging the right tools for the right job and understanding the strengths and weaknesses of your stack. You use the JVM for the heavy orbital physics, you use Python for the clean data flow and fast iteration, and you use vectorized CMath to save your CPU from melting.
Let's take a step back and just marvel at the journey we've mapped out here. You, the listener, now have the complete end-to-end blueprint for building a tracking project that would have required a supercomputer 20 years ago. You start by spinning up that Java virtual machine inside your Python script. You feed it the lumpy potato ZIT file so the blind physics engine can actually perceive the real wobbling Earth. You anchor your timeline to an absolute atomic clock to dodge leap seconds, and you anchor your space to a non-spinning inertial frame so your math is clean.
Right, perfectly clean math.
Then you parse a 1970s punch card TLE text string. You fast forward the sky using the mathematical elegance of SGP4 analytical propagation. And finally, you run a broad phase filter to find the danger zones, zooming in to predict the exact mist distance between two satellites.
Moving from downloading a zip data file to predicting highly dynamic orbital collisions in a local environment. It is an incredible amount of power to have at your fingertips on a standard commercial laptop.
It really is. And to think, we started this deep dive talking about how programming is usually this neat, contained sandbox, but the sandbox we just learned how to build it contains the entire Earth and every piece of human engineering orbiting it. But as we wrap this up, internalizing all this math and architecture makes me think about the sheer physical scale of what's happening above our heads.
It is a scale that is accelerating at a rate that is difficult to fully comprehend. And that leaves us with a critical, somewhat daunting question to consider as you start writing your own code. We are entering an era where low Earth orbit is becoming deeply congested. We're seeing the launch of mega constellations, tens of thousands of new satellites being deployed in a matter of years, fundamentally altering the physical density of space.
The sky isn't just getting crowded, it's getting packed.
So consider this what happens to our local computational limits when the sky is so incredibly crowded that your broad phase filter is constantly triggering.
Oh, wow, I hadn't thought of that.
Right. What happens to our systems when a 10-kilometer safety threshold is constantly being breached by thousands of objects simultaneously, triggering endless fine-phase searches that bog down the CPU? At what point does avoiding catastrophic collisions in space become less of a physics problem and more about the absolute limits of computer science and hardware processing?
A truly fascinating problem to ponder as you fire up your IDE and initiate that virtual machine. Until next time, happy coding and keep looking up.